finished last time, as I stated, the interpolation lemma, which I'll restate here. Which says the following things, that for, suppose that we have a neighborhood in the complex plane, let U be a neighborhood of a path connecting 0 and 1. And then I said that then there is a constant gamma, which depends only on that neighborhood. It's a positive real number such that whenever we have a polynomial of degree n, so here I'd like to have n at least 2, such that this polynomial is non-zero in every point of the neighborhood. So for all z in the neighborhood, then to estimate it with a relative error epsilon, to estimate its value at 1, then for any epsilon between 0 and 1, the value of P of 1 up to relative error epsilon is determined just by relatively few lowest coefficients. So is determined C sub k was k, let me write it here, still have some space, not exceeding that constant times log n minus log epsilon, right? So that was the statement. And we mentioned, so when I say is determined, that means that if you have polynomial of that type and you just tell me the first relatively few coefficients, then I can figure out the value of that polynomial at 1 with an error epsilon, right? And we had this picture, so there was a path going from 0 to 1. There was a neighborhood of that path where the polynomial was non-zero, right? So just to make sure we are on the same page. So no objections? Okay. So what I'd like to do, I'd like to sketch the proof because it's really simple. I mean, it's more or less just a useful, sort of trivial but useful remark, right? So, so proof, I'll do it here. So first, let's do a particular case when the neighborhood is just a circle. So special disk rather. So special case. Then U just a disk. And since it's a neighborhood of 1, 2, so it has to, the radius of the disk has to be greater than 1. So the picture, therefore, is as follows. So this time, in that special case, what do we have? So we just have a circle. So somewhere here is 0. Somewhere here is 1, and the radius of the circle is greater than 1. What do we do then? So we say that, okay, so we have this polynomial, p of z, so it's non-zero in the circle, so we can take a branch of the log. So let f of z be the log of p of z, right? So then I can take the Taylor polynomial of this function. So let t sub m of z be the Taylor polynomial of degree m computed at 0. So it's f of 0 plus the sum from k equal 1 to m, the k's derivative at 0, right, divided by k factorial and multiplied by z to the k. Right. So I will use this Taylor polynomial actually to estimate the value at 1. So I make two claims, both kind of trivial. So the first claim is that if I try to approximate the value at 1 using this Taylor polynomial, then I can bound the error by something like this. So n over beta to the m, beta minus 1, m plus 1, from which I deduce that to get error, additive error, epsilon, it suffices to take m just logarithmic, where the implicit constant in the O notation depends on beta only, right, because the error goes down exponentially. So, and the second claim is that whatever I need to compute this Taylor polynomial just depends on the few coefficients of this polynomial, so that f sub 0, f prime of 0, f sub m of 0 are functions can be computed from c sub 0, c sub 1, c sub m. So once I have this, I'm done, right? So I just approximated this value at 1 of the log with an additive error epsilon using some combination of like logarithmically many lowest coefficients of the polynomial. So, okay, fine. So, well, claim 1 is easy, while claim 2 is also easy. So claim 1. So what I have? So I have a polynomial, I can factor it. Right, where alpha i's are the roots. So right, but there are no roots outside, inside the disk. So I must have really the absolute values at beta, right? So then, right, then I can take the log. And I know very well how to approximate log by a Taylor polynomial, right? So log of 1 minus z over alpha I, well, is the sum k equal 1 to m, right? Z to the k over k, right? Alpha I to the k, and that's for, of course, z not exceeding 1 in the absolute value. But alpha i's all greater than beta, so plus little something. And I know how to estimate this little something because it's really the sum of geometric series, well, more or less. So at right, and when I do that, I'll get the error that I promise I get. And then I'll just take the sum of all these approximations overall, all the roots, and I accumulate the factor n, right, upstairs. Right. So any objections to this exercise? So claim 2 is just as easy. So how about I still have room there? I'll do it. So claim 2. Well, that's basically how you relate moments to cumulants, right? So I'm interested in the derivatives of the log. So f prime z is p prime of z over p of z. So therefore, p of z is p prime of z is f prime of z p of z. Therefore, if I differentiate that k minus 1 times, so I'll get p sub k at 0, right, is the sum from j equal 0 to k minus 1, k minus 1, choose j, then I differentiate pj time, and f I differentiate k minus 1 minus j, so I get k minus j 0. And that's a system of linear equations with triangular invertible system of linear equations. So solve for f sub k at 0 in terms of p sub k 0, right? So that's what we do when we recalculate cumulants in terms of moments and the like, right? So that does the first case, right? So the special case, right? So having done the special case, we do what? The general case, right? So the general case well, what we do, we construct a disk of some radius beta greater than 1 and some auxiliary polynomial phi that does the following thing. So it maps the disk inside the neighborhood, but maps it with some precision so that 0 goes to 0 and 1 goes to 1. And then what we do, we apply the special case to the polynomial, to the composition, to P of phi of z. So what happens now, so let me draw an arrow here. So what happens now is that the composition now is non-zero on the disk of a radius greater than 1, right? And we want to estimate its value at 1 because phi of 1 is 1, so we substitute 1, we get pure 1. From very few, logarithmically many coefficients at 0, right? But since it maps 0 to 0, so the lower order terms in the composition cannot come from higher order terms in the polynomial. So they only have to come from the terms of lower degree, right? And therefore, it suffices to have this many terms. So what changes here in this composition is that degree n. But it's under the log. It changes, sort of, however it changes. It's one polynomial for a given neighborhood. And that's a proof, right? Okay. Yeah, I'm a bit weak in topology. Like, what if it gets kind of thin or something? So I just want to have a path. Yeah, so. I leave it to the experts. If they say it is, that'd be. Yeah. So it's easier to work with a path. In fact, sort of a, or should I say, morally easier, because what happens here? You really want to follow some chosen path and see if there is nothing around. More or less, yes. Okay. So basically, the moral from here. So moral. What's this gamma fu? So what's the order of this coefficient? So gamma fu roughly one over beta minus 1, where beta greater than 1 is the radius of the sort of largest disk that can be mapped holomorphically inside the neighborhood, so that 0 goes to 0 and 1 goes to 1. Right. That's the moral of the story. That's the generic meaning of this constant. Well, the point is, it doesn't have to be conformal, right? It doesn't have to be 1-to-1. It can, in principle, it can squish this disk, right?
No, but I mean that best constant, is that related to the distant image, the distance from the image of 1 to 0 in this map?
Is it like cartesian or something, or? Okay, so how about I give several examples, right? So okay, So that's, yeah, thank you for the question. So that smoothly brings me to the couple of examples I'd like to discuss. So the first one, what if the neighborhood is really skinny? So what if U is just the sort of the delta neighborhood of an interval, of the interval, so delta. So the picture is I have an interval and 0, 1, and the neighborhood is just pretty economical, right? So then it's not hard to figure out that this constant is actually, well, pretty large. It's exponential in 1 over delta. You cannot do better. You can do worse, of course, but so you cannot do better. It's Schwarz-Lemma, basically. So you cannot do better. So the second example, what if the neighborhood is really, really big? So it's a half plane. So what if I have something like this? So the picture is 0, 1, the interval, and the neighborhood is really this half plane. So, and this is minus delta. So then the constant goes down sort of exponentially. So it's something like O of 1 over delta log 1 over delta. You can still kind of put a larger disk. But the most interesting example that I'd like to spend some time on is what if the neighborhood is really huge? So that's the third example. So what if the neighborhood is basically the whole plane? Well, it can't be the whole plane because the roots have to be somewhere. So minus the ray in the negative direction. So the picture looks like this. So the neighborhood, so we have 0 and 1. We have this pretty much everything. Yeah, with the sole exception of sort of real ray in the negative direction. And the neighborhood is this. So then the constant becomes 1 over square root of delta log 1 over delta. So, okay. So these three examples, if I think, kind of pinpoint various things that are going on here. And they are, of course, optimal, right?
But it is, your definition implies that it is a conformal invariant of this region U with good points.
Conformal, why is it conformal? But point go to points. That's very restrictive.
That's right. So
yeah.
It's a conformal variant of that configuration. So it can be computed.
Yeah, it can be computed. So I computed it. So, yeah. So there are these. Yeah. So no, sure. I mean, there is no. Right. Yeah, that's exactly right. And that the sector opens. Right. So for. Yeah, so for me, right, that's the most interesting interpretation because situation because here there is this map that kind of opens the disk as a fan that covers everything, but it piece of the negative ray. So, okay. I'd like to do something with this. And what I'm going to do, I'm going to apply it to perhaps the best studied model, well, in combinatorics and statistical physics, that what combinatorials call matchings, and what physicists call monomer dimer model. So, we'll erase the stuff. So matchings slash monomer dimer model. Right, so what do we have here? So we have a graph. Right, so has vertices and edges. And we are interested in matching, so the set of edges, say, let's call it M. M is a matching. If every edge from that matching is incident to at most one vertex, right? So if every vertex is incident to at most one edge from M, every vertex is incident to at most one edge from M. So the picture is, well, something like this. So we can pick this edge, we can pick that edge. We can pick some others. So an empty set is always a matching. So it's a matching. So then what do we do next? So we look at what combinatorialists call the matching polynomial. It's basically the generating function, and statisticians call the partition function in the monomer dimer problem. So where m sub k of g is the number of matchings with k edges, right? And what do we know about this polynomial? There is a remarkable result by Lieb and Hellman, right? So Hellman and Lieb. Of 1972, which says that all roots are real and do not exceed -1 over like 4 delta minus 1, and what is delta? It's the largest degree of the vertex. So degree of a vertex. So then we are in the situation of example 3, right? So if we want to estimate the total number of matchings right? So the number P of 1 of matchings of all sizes is determined up to relative error epsilon by the numbers of matchings of very small size by m sub k of g for k of the order of 1 of a square root of the max degree log of the number of vertices divided by under the log by epsilon, right? So that's an example of sort of interesting, I think, flexible rigidity or rigid flexibility. So if you care about the total number of matchings up to an error epsilon, what do you have to tell me? You just have to tell me the number of matchings containing k edges with k relatively small. So it's square root of the largest degree times the log of the number of vertices, right? And they somehow pin down up to the error epsilon the total number of matchings, right? So I have no idea what they do, right? So no, I don't know. I mean, that's something. Yeah. So I chose this example on purpose because that's the model very well started, right? And everything's known about it, right? But not this. So that in fact there is some, as I said, some sort of flexible rigidity there. That to get the whole set, you just have to know these numbers with relatively small k, right?
So what about, I mean, this is sort of shot in the dark, but like if you take a CNF formula, there are all of these properties like, the number of, common things where you only have a logarithmic number of monomials. Together, those counts about how many satisfying assignments determine the overall.
Apparently, they must be related. Yes, I know what you're talking about, right? So yeah, right.
Because it's some of the same
Nissan, right?
surprise
Samarodinski, right? So they must be related. The issue, I don't know how. Right? So it looks like they should. Although there is go to like square root of n, right?
Yeah.
Here's logarithmic, right? It's even worse or better, right? Okay. So other concerns?
You don't know these small numbers of matchings exactly. Can you still say?
Yeah, you can, but you have to know them with, well, you saw the proof, right? So you just look how the errors accumulate, right? And yeah, so it does give rise to an algorithm to compute the number of matchings that, surprise, surprise, has the same complexity as the algorithm based on correlation decay. One of the authors is here, so David, right? Nair, right? Also Prasad, Bayadi. Did I miss? I tell you, yeah, I know them all. Yeah, yeah. Bayadi, Gamarni, Katz, Nair, Titali. Right. So why does it match the complexity of the correlation decay? I have no idea, but it does. Right. So, okay. So other. So they say, it's not my saying, that every talk should have one proof and one joke, and they shouldn't be the same, right? So I already given one proof. I sort of intend to give another proof. That's more like a joke. So did anyone prove my theorem 1 from yesterday with 0.5? So I feel like showing you the proof, okay? So the reason I feel like it is because after we've done all that, it's clear that the issue is now to develop techniques where we can sort of prove zero freeness. And the most general technique that I could think of is called induction. So it almost never gives sharp bounds, but it's sort of applicable in a variety of circumstances. And that's what I'm going to do now to show how it works for the permanent. So recall theorem 1. So if Aij is n by n complex matrix with distance from one of the entries not exceeding 0.5, then the permanent of A is not 0. So proof. So as I said, induction by n. But we will induct a slightly stronger statement. So if A and B the matrix is just like there, with entries within distance 0.5 from 1 and differ in at most one row or column, then not only their permanents are not 0, but the angles between permanents is at most pi over 2. So what is an angle between permanents? Well, permanents are vectors, right, on the plane. Despite that you might have been taught that they're vectors in the tangent space to the plane, they're actually vectors in the plane. Okay? And therefore, we can measure the angle. Right, and that's what I'm going to prove. So, okay, so how does it go? So for n equal 1, the situation is quite clear.
So was that the joke?
It's one. Well, I leave it to you to figure out. It's not my joke, by the way. You probably recognize the author, right? So it's Arnold's, right? So clear. Because what happens here is. So there is a circle, center at 1, there is this 0, there are 2 points, A and B, and the angles not only doesn't exceed pi over 2, it doesn't exceed like pi over 3. So how do we go from n minus 1 to n? So what do? We use the first row expansion. So the permanent of A, so suppose that A and B differ in the first row. So suppose that A and B differ in the first row. In the first row. So then I can expand, right? So I can say that the permanent of A is the sum over the linear combination of permanental minors, which are obtained from matrix A by crossing out the first row and j's column. And the permanent of B is a different linear combination, but of the same permanent minors, because only the first two rows differ. Now, I look at the minors, and what do I notice? That any two minors differ in at most one column. Right. So AJ1, AJ2 differ in one column. So therefore, by the induction hypothesis, not only the permanence is non-zero, but the angle between the permanent of AJ1, which is not zero, and permanent of AJ2, which is not zero, doesn't exceed pi over 2. So what's left now is what I call a middle school geometry. It's just a simple geometric lemma. So permanents are gone by now, right? And we're just dealing with vectors in Euclidean plane. So plus little lemma that if you have a bunch of vectors that are non-zero, and if you have a bunch of numbers with distance 0.5 to 1, then for the linear combination and for the other linear combination, we have that they're non-zero. They then on zero. Oh, right. And the angle. Thank you. And the angle between any two doesn't exceed pi over 2. Then for the linear combination, we have they're not zero, and the angle doesn't exceed pi over 2, which completes the proof, right? So that's this theorem is probably the best I did for the last like 5 years, maybe ever. I sort of like it. Yeah, it gives you absolutely no idea whether this 0.5 is optimal in any sense. It's optimal for this type of proof. So we apply it as follows. So U sub j is a permanent of A sub j, the permanent minor, and alpha sub j is A1j, and beta sub j is B1j. Right. So these are linear combinations of the same vectors that form an angle at most pi over 2. Oh, come on. You can do it. I trust you can do it. Yeah, so it's triangle inequality. Yeah.
But you look at this inequality as 1 minus aij less than or equal than 0, 5, and for this proof it is optimal.
Yes.
Is there a larger region of values of a which is larger than this for which you can still run this?
Yes, there is. Thank you for the question. I'll show you. in a minute. So it will not be round shaped. It will be a strip. Right. So you can. Well, I mean, largest, they're incomparable in some sense, right? So one is, what we did, so we did this, but what I'll show you in a second is that. So, no, actually no. So that will be 1, 0 will be here, and here will be somewhere 2. I'll show you that. Yeah. So prove absolutely the same way. So prove the same way. So suppose that Aij is a matrix n by n, where I allow my real part to come as close to 0 as I want, but stop at some particular point. So Aij, the real part between delta and 1 for some fixed delta. But then I have to pinch the imaginary parts. Something like this. So then the claim that the permanent is again non-zero and through this interpolation, which means it means that the permanent can be approximated slightly smaller, thinner strip. Right? So permanent efficiently approximable. I can divide delta by 2, right? Yeah, I can put 10 there, right? Yeah. So it's the 0 that matters, right? Yeah. Okay. So right. So the Monte Carlo Markov chains here, in the real case, do much better, and I'll try to sort of discuss it tomorrow. So what's going on there, and also connect it to phase transition that was barely mentioned, I think, today when I mentioned the Hellman-Lieb theorem, which basically asserts that there is no phase transition at positive temperature of the monomer-dimer system, right? So what I'd like to say that, I mean, I've been proving this theorem several times. At first, I used some math, and I got really bad constant. Then I used a little less math, and the constant improved, and that showed me the way. So here I use, I think, as little math as I possibly can, but I'm still, well, not sure that that's optimal. Maybe there is something that I'm still overusing something here. That if I drop it, I got the best constant. So that last step I couldn't do. What I'd like to say is that this sort of inductive argument, however simple-minded, apparently sort of runs a reasonable mileage. I'll just give you one example of a very, I have some like 8 minutes or so left, of a very general partition function that covers sort of multi-spin systems, and combinatorialists call it the graph homomorphism partition function. So maybe I'll go down there. So graph homomorphism multispin partition function so it covers, for example, the Potts model, therefore the Ising model, and the like. Yeah, so we again have a graph. And to every edge, a certain complex matrix is attached. Edge UV attach a complex matrix A U V I J, well, A U V I J, symmetric, right? Complex symmetric. So this multi-spin thing, graph homomorphism, is the following creature. So for this family of matrices, what we do, we take the sum over all maps of the same, I should have said, of the same size, a complex symmetric K by K matrix. So we take the maps into the set from 1 to K, which we consider as like we color the vertices, right? And then what we do, we take the product over all edges in the graph, right, of the corresponding matrix elements. So this is really quite general creature. So it can color, it can count colorings, it can count independent sets, it can count, it contains the Potts model, contains more or less, I think, everything yeah, that accounts for pairwise interactions, right? So theorem, which I proved with Pablo Soberon, actually using some math, and that's why we didn't get the best constant. So after I reproved it using no math at all, and I got a better constant. So there is an absolute constant gamma greater than 0. I know that I can choose 0.55 such that this function is not 0 provided all elements are sufficiently close to 1 again, but the distance should change with delta, where delta is again the max degree of a vertex. So here is a situation. So the proof that I have, basically it's pretty much the same. So this type of induction. So you just find your versions of permanental minors, which is done just by sort of pinning down some of the values of this function on some of the vertices. Right, so but the situation here is kind of a bit more interesting. So again, so what we have here is we prove the existence of a disk, right? Zero-free disk. We can prove the existence with a better constant of a strip around the disk. But 0 is off limits. We cannot go arbitrarily close to 0. We don't know it yet, but we know for sure that there is some bound, unlike in the case of the permanent. There is some bound that we cannot extend this strip into, because the problem becomes sharply hard. So we don't know the optimal extension of the strip, but we know that we cannot stretch it all the way to 0, unlike in the case of the permanent, there we can sort of go arbitrarily close. Even to approximate, right. And yet they behave differently. Yes, because they behave differently. Yes, that's exactly right. So, okay. I think well, permanent maybe not. No, but matching certainly, like matching. Yeah. I can put some other constraints here. Still, theorem will still hold and will contain permanent. But yeah, so it's pretty much covers all like physics, pointwise interactions, so multi-spin. And by the way, so the interesting thing, I think, well, I don't know, well, it looks to me like an interesting thing that the bound does not depend on the number of possible spins on K, on the number of colors, which means that it's effectively that if K can be chosen like infinite, like in Heisenberg model, like continuous families of spins. And it's still true. So I have 1 minute left, so I will not write anything more. But so what is it good for? Computationally. So suppose that we want to, for example, count proper coloring. So the number of ways to color a graph so that no edges have two vertices colored with the same color. So that's already sharply hard, and yeah. So, but instead, and that corresponding to computing this function at some particular matrix or family of matrices with zeros and ones. But instead of throwing our hands and saying, well, the problem is hard, we are not going to do anything with it. So what we do, we replace all zeros by something close to 1 on the lower side, and all ones by something close to 1 on the upper side. And what we say that we now we count all colorings, legal or not, but illegal colorings are weighted down exponentially with the number of miscolored edges. And that's something, right? It's better than saying that the problem is hard, so forget about it. Right? So that sort of gives you some smooth version that's still solvable. Okay, so I think, yeah, that's my time is up, so that's it then. Thank you.
Any questions? Any objections?
Yeah. Well, you can try to play with it, and I found that pi over 2 is sort of gives you the best constant in the end. But yeah, sort of I welcome any information you can provide on the constant.
So actually related to the same, if I went to say 1/4, would I get some effective bound on how far the permanent is from 0 for a given n?
I'm sorry, so where's 1/4 come from?
Just type in the constants rather than putting 0.5, I put 0.2. And I put 0.2 there. And can I actually get a disk around 0 in which I'm sure that
No, but if it works for 0.5, then it should work for 0.2. No?
that's about lower bound for the absolute value of the permanent.
Oh, the absolute, yeah, you can get a lower bound. You can get a lower bound. It's a sort of, from this proof, the lower bound that you get is exponentially smaller than n. Yeah, but which doesn't mean that it's a true lower bound, right? But that's coming from the proof.
And if you do the proof, that would probably consist in extending the interpolation of the permanent of an interpolation of the permanent, which is, I mean, that's
That's what I'm doing, right, more or less, right? So.
well, you're using
Oh, you mean like the cluster expansion?
yeah, I mean
Cluster expansion, right? Yeah, it's called clusters. Yeah.
I don't know. Yeah, I tried this, but I didn't get 1/2. But if you like put log of
Yeah, I don't think it works at all.
I see.
Yeah, I think he just if you write this series, it just diverges somehow.
For permanent.
Yes, for the permanent.
But for what if you do it for log of permanent?
For the log, yeah, that's what I'm saying. For the log, for the permanent, right? I think it diverges.
Okay.
Yeah. People checked, I think.
So in this last theorem, I believe, so if the graph is just a cycle,
Yes.
then it is a trace of the product of matrices. Is
Um,
this theorem
this
easy in this case?
cycles.
Is
It must be.
something interesting in that?
Well, it must be easier, right? So things algebraic generally easier. Invariant things are easier, yeah. But yeah, so cycle. I don't know. Yeah.
Yeah, I have a question. So you have two regions, I mean, the family of regions here that work. And is there any conditions, if I give you a region, to put conditions for which, equivalent to be
Approximate. I'm not sure. I don't know how to do it sort of mechanically. I'll probably have to think, and sometimes I'll have to tell you that I don't know. So I can prove it for some regions, and I cannot prove for some other.
But it's no, there is no conditions on the regions that you use that you need to. That you cannot spell out the conditions.
No. I can only say that for sort of computational purposes, I do prefer streaks to disks, right? Because they kind of allow me to go further along the real axis that I kind of enjoy doing. Well, I can include zeros, of course, for different. So, for example, for diagonal dominant matrices, I can compute permanence, right? Those include zeros, right? But that uses so the same uses a different argument for zero freeness. So the moment you have zero freeness, you have a filled day there, right? So the trouble is to prove zero freeness.